Okay, so we've successfully invented an integral that we feel represents the flow of a vector field along a path. So let's go ahead and compute a couple of these. Right? So our general idea for what this flow integral should be is the integral of f dot unit tangent ds. But when we go to parameterize it, we'll use one of these versions, usually this one, right? Because when you actually go to calculate dr, it turns into this anyway. So to actually calculate things, we'll use this definition of a flow integral. Okay, so let's start out with this example, finding the flow of this vector field. Oh, why do I have a star here? We'll find the flow of this vector field along this curve, t comma t squared for t going from 0 to 2. We can actually sketch what this curve is doing, right? This is really just parameterizing a parabola that starts here at 0, 0 and then goes up here to 2, 4. So something like this. And just looking at how the vectors are oriented compared to the curve, it looks like the vectors are mostly pointing along the curve. So we expect that when we compute this flow integral, we will get a positive number. So let's just check that that happens, or check if that happens, I guess. So we're going to compute the integral of f dot capital T ds, which is the integral from 0 to 2 of f dot r prime dt. So integral from 0 to 2 of, now when we write down f, right, this is our vector field, but remember part of parameterizing the integral is telling the vector field where you are at any particular point, right? So here where the vector field is minus x squared plus y, we're going to use the x and the y functions coming from our parametric curve. So minus x squared, x is t in our parametric curve, so minus t squared, plus y, but y is t squared, so like this. Okay, so that's the first component of our vector field. The second is x times y, and that is t cubed. Right, so don't forget that when you are finished parameterizing your integral, your line integral, it ought to be a function just of t. If you have x's and y's lying around, you probably forgot to plug in your coordinate functions from your parameterization. Okay, so that's f. Now we need to write down r prime. So we need to differentiate our parametric curve, and that's 1 comma 2t dt. Okay, and now we have to compute this dot product. So this is, actually that's 0, isn't it? So this x coordinate is 0, so when we do the dot product, we just get 2t to the 4th dt. I can see already that this is going to come out positive, which is good. That's what we wanted. So now it's a regular single variable integral. Now we just do what we usually do with our integrals. Antiderivative is 2/5 t to the 5th. We need to evaluate at 0 and at 2. Let's see. 2 to the 5th is 32 times another 2 is 64. So 64 over 5. I hope I did my arithmetic correctly. Anyway, it's positive, right? It's positive. Okay, so to calculate the flow integral, we parameterized it in terms of our vector field and our parametric curve. That turned it into a single variable integral, which we evaluated in the usual way. All right, let's look at one more example. Let's find the flow. Now this example is in 3 dimensions, and we haven't talked about 3 dimensions before for this flow integral. But if you look at this, at both of the versions of a flow integral that we wrote down, right? There's integral of f dot t ds, and then there's the integral from a to b of f dot r prime dt, d little t. Neither of these depend on being in 2 dimensions, right? Both of these make perfect sense in any number of dimensions. So we can do this in 3 dimensions just the same as we did in 2 dimensions. So to find the flow of this vector field along this helix, right, in the x and y direction, this is going around a circle, but in the z direction, it's going up at a constant rate. So this parametric curve is a helix, right, just going like this. And we're going to do this, find the flow along this helix for 1 turn, right? We're going from t equals 0 to 2 pi, so that's going to be just 1 loop of the helix. All right, so we're going to integrate from 0 to 2 pi f dot r prime dt. So it's integral from 0 to 2 pi of, now it's going to get a little tricky when we start plugging in all our coordinate functions into this. So minus z is t, right, so that's z, times y, and y is sine t. Okay. Now we need z times x. Z is t, and x is cosine t. And then we need x times y, and that's cosine t times sine t. Okay, dotted with, now we need r prime, which is going to be minus sine t, comma, cosine t, comma 1, dt. Okay, so things look bad at first, but right, persevere. Let's see. In the first component of this dot product, we get t sine squared t, okay, plus, and then in the second part of the dot product, we get t cosine squared t, plus, and then in the third part of the dot product, we get cosine t sine t. Okay, dt. All right, this looks a lot better now because with the sine squared and cosine squared parts, right, we can factor out a t to get a sine squared plus cosine squared, but sine squared plus cosine squared is 1. So this is going to give us the integral from 0 to 2 pi of t plus cosine t times sine t, but that's 1/2 sine 2t, right? And so this is going to be straightforward to integrate. So this is, let's see, antiderivative of t is 1/2 t squared. Antiderivative of 1/2 sine 2t is minus 1/4 cosine 2t. You can check me on that, but I'm pretty sure that's right. We need to go from 0 to 2 pi. So when we plug in 2 pi, we get 1/2 times 2 pi squared minus 1/4 cosine of 4 pi minus, and then plug in 0, we get 0 minus 1/4 cosine of 0. But then these parts cancel. So we're just left with, let's see, 1/2 times 4 is, so 2 pi squared. So 2 pi squared for the whole thing. One thing sort of weird about flow integrals is what the units turn out to be, right? So unless our vector field represents something in particular, how I usually think of a vector field is as a velocity field. Right? It's telling me how fast some fluid is flowing around. And velocity fields have units of meters per second because they represent velocities. Okay, so this f here has units of meters per second. Okay, this tangent vector doesn't have any units, right? Direction vectors are unitless because, right, remember, the reason why that happens is because capital T is r prime over the length of r prime. So if r is measured in meters, then r prime is measured in meters per second, but the magnitude of r prime is also in meters per second, and those cancel. So this unit vector t doesn't have any units. And then ds, well, ds is an infinitely small speck of arc length, s, and that's measured in meters. So when we integrate, we get something in meters squared per second, right? Which is a little weird. So it's the reason that this happens is because, right, how you should really think of this is not as meters squared per second, which makes it look like an area per second, and that's not really what this is representing. You should think of it instead as meters per second times meters. So this meters per second is here because we're measuring a flow, and so how rapidly the fluid is flowing is part of our units, and that's what the meters per second is doing here. But also, another part of what we're measuring is how long the curve is that the fluid is flowing along, and that's why this meters is here. So this meters times meters isn't really representing an area. It's here because there's a velocity and also a length in the thing that we're measuring, and so those units get multiplied.